We're going to start out this video the way we have so many previous ones, with writing our order of reactivity up top. Acid chlorides are first, anhydrides come next. And now that we have talked about class 2 derivatives, then comes aldehydes and ketones, then esters, amides, and nitriles. Carboxylic acids over to the side, but about equal reactivity to esters. We're going to talk about hydride donors next, which is another way to make an alcohol out of carbonyl compounds. There are various hydride donors. Here are some examples, but this list is not exhaustive. But these examples are varying in strength. One thing I want to point out about these reagents before we get into the specifics of them is some of them have boron and some of them have aluminum. Aluminum is more metallic than boron. Aluminum is less electronegative than boron. So because of that, the aluminum-containing hydride donors are more reactive than the boron-containing hydride donors. So aluminum ones, stronger reducing agents, borons, weaker reducing agents, but there's still a spectrum among them. Let's see some examples first. Here are a couple of things that we shall reduce. Let's draw it on paper. Starting with that first reaction, we're reacting with sodium borohydride. This is a thing you have heard before, sodium borohydride. It's an ionic thing with a negatively charged boron. The way it works, it's a hydride donor. Hydrogen means hydrogen, hydride means hydrogen with its electrons, hydride. Attack the carbonyl carbon, like so. We get an H attached to the carbonyl, what used to be the carbonyl carbon. And then that O- gets protonated. This one gets protonated from the solvent. It's common for us to do acid workup in these, just like we did acid workup in all of those Grignard reactions. But this one didn't need acid workup because I added a protic solvent to my mixture. So sodium borohydride is weak enough that it can exist in the presence of a protic solvent. Those aluminum things should not be in protic solvents. They have to be in aprotic solvents or else you're in trouble. So boron stuff can be in protic solvents, aluminum stuff, not so much. Note, I have color-coded the hydrogens over here. This purple one that's attached to the carbon came from the hydride donor. This green one over here came from my solvent, or sometimes comes from acid workup. This specific one came from the solvent though. Be sure you know which H comes from where, because it's typical for these reactions to be done with isotopes so that you can identify which carbon came from where. That's sodium borohydride reacting with a ketone. Up next, sodium cyanoborohydride. Cyanoborohydride. And an aldehyde. Whoops. As it turns out, sodium cyanoborohydride does not react with aldehydes, but it does react with these things. What is this thing? This is an imine, an imine. So let's go back to our reactivity chart real quick. We have said boron things are less reactive than aluminum things. As it turns out, there's a line, and sodium borohydride can reduce everything above that line, but it's too weak to reduce anything below that line. Lithium aluminum hydride LH4. Lithium aluminum hydride can reduce everything on the entire chart. Nitriles and everything above. Well, sodium cyanoborohydride is weaker than sodium borohydride. Replacing one of the hydrogens with a cyanide causes it to be even weaker. So as it turns out, sodium cyanoborohydride cannot reduce an aldehyde. It's actually too weak to reduce an aldehyde, but it can reduce anhydrides and acid chlorides. It can also reduce imines, imines. So an imine falls here in the order of reactivity as far as hydride reducing agents go. It doesn't generally fall there in other reactivity, but sodium cyanoborohydride can reduce an imine, can reduce an anhydride, can reduce an acid chloride, cannot reduce aldehyde or anything weaker. Sodium borohydride can reduce all of it. So, back to where we were. Aldehydes cannot be reduced by this. It's too weak, actually. So, we're going to pretend all of this is stirring together in a reaction flask for a reason we will see soon. And sodium cyanoborohydride is only capable of reducing this. So we got an Na+, a B with 3 H's, and a cyanide. This is a weaker hydride donor than borohydride, but it can still attack the carbonyl carbon. I put air quotes around that. You just couldn't see them. This H, this carbon already had one H, and now it got a second H. This N- can then take a proton from your solvent. What's the big difference in this example and the top example? Not much. You get the same thing overall in general, but this time we're reducing an imine instead of a ketone. So we get an amine as a product instead of an alcohol. The principles behind it are the same, but cyanoborohydride is too weak to reduce an aldehyde. So if you really had all of this stirring in solution together, in the end, you would have leftover unreacted aldehyde in your final product solution. All right, next. What if I have multiple functional groups, multiple things capable of being reduced? Well, you're going to reduce them all because every one borohydride is capable of reducing 4 carbonyls. We're going to reduce both of them. We get a new purple H from my borohydride. We get a new green H from my acid workup on those two things. As long as you put at least half as much of this as you have that, you will get this product. Because every one sodium borohydride is capable of reducing 4 carbonyl compounds. What if you wanted to have a little more fun and use something a little more dangerous? Lithium aluminum hydride, same dang thing. It's capable of reducing aldehydes and ketones. It reduces them both. If I reverse my colors this time and say these green H's came from lithium aluminum hydride, the purple comes from water. Lithium aluminum hydride reduces both. For every one of these molecules, you can reduce 4 carbonyl compounds. Lithium aluminum hydride is crazy reactive. It will do that in a heartbeat. One little thing of note while we're talking about it being a little crazy, here I added acid as workup. Here I added water as workup because lithium aluminum hydride and acid, not a friendly combination. Watch out. Moving right along, what about carboxylic acid derivatives? Can they be reduced with hydrides? Does it react a lot the same? A whole heck of a lot the same. But what's the biggest difference between a carboxylic acid derivative and an aldehyde and ketone? A leaving group. So you attack the carbonyl carbon, just like always. Get your new hydrogen added. But this is an anionic tetrahedral intermediate with a good leaving group. So fold it down and kick out your weakest base, your best leaving group. And here we have an aldehyde. Can aldehydes react with sodium borohydride? So for every one borohydride, you can reduce 4 compounds. So we've still got plenty of borohydride in solution. There's going to be some other stuff that happens with it, but mechanistically, it's easier to start over with a new BH4. But there's some other stuff that might be happening. Attack the carbonyl carbon again. Make an O- again. And then you do your acid workup. Where does the pink hydrogen come from? The acid workup. Where do the blue hydrogens come from? Your hydride donor. Why is that a big deal? Why do I care? So that was an acid chloride. That's the most reactive acid derivative. What about esters? They're less reactive. Yeah, they are. What that means is sodium borohydride cannot reduce them, but lithium aluminium hydride can. Attack the carbonyl carbon. It works oh so similar to all the other stuff we've seen. The difference in class 1 and class 2, I have a leaving group. Fold down and kick out my weakest base, my best leaving group. I get an aldehyde. Lithium aluminum hydride. For every one of these, you can reduce at least 4 things. You have 4 hydrides that can be donated. So you can donate another one. I'm going to rob it from over here, which is a little bit illegal, but you don't mind. 2 hydrogens over here and an O-. And then I do my workup. It's water workup here, not acid workup, because you don't want to dump acid into your lithium aluminum hydride. It will not be a fun time. Ta-da! I made an alcohol here. I made an alcohol up here. Both of them are primary alcohols because I had a leaving group. Attack once, fold down, kick out. Attack again, pronate. I made primary alcohols with these class 2 derivatives because they had a leaving group. Okay, cool. I think I may have just called these class 2 derivatives. That was a boo-boo. I didn't mean that. These are class 1 derivatives, carboxylic acid derivatives. So I made a primary alcohol out of both of these. In the bottom one, lithium aluminum hydride is my only choice because sodium borohydride is not capable of reducing an ester. Sodium borohydride is not strong enough. Okay, cool. What about carboxylic acids? Can they be reduced as well? The mechanism is a little more convoluted. And so rather than paper, I actually am presenting it to you on PowerPoint. Lithium aluminum hydride is a hydride donor. Hydride is a strong base. When you react lithium aluminum hydride and a carboxylic acid, the first thing that happens is you must deprotonate your carboxylic acid. Deprotonate your carboxylic acid up here to make a carboxylate. We've seen one other thing capable of reacting with a carboxylate. That was an organolithium. Lithium aluminum hydride is number 2 thing that can react with a carboxylate. And it reacts like so. I said a minute ago, and may have confused you how I said it, there's some other stuff that really happens when you add these guys, as in like this. At this point, aluminum only has 6 electrons, 3 electrons, so it's a Lewis acid at this point. So it can share electrons to actually become connected to one of your oxygens on your carboxylate, like this here. That really does happen in most of these reactions, but we can get away with drawing the mechanism without involving that, except we can't get away with drawing the mechanism without involving that for this carboxylic acid reduction. So the aluminum oxygen bond here wants to stay. That's a very strong bond. So we fold down and kick that out as a leaving group to make this aldehyde. Can lithium aluminum hydride attack an aldehyde? So we do another typical attack the carbonyl carbon here, even though I've not drawn that. Attack the carbonyl carbon and then protonate with some water aqueous workup later to get the final primary alcohol. So if you look back, acid chloride reduction made an alcohol, that was primary. Ester reduction made an alcohol, that was primary. Carboxylic acid reduction makes an alcohol, that's primary. Because all of those things have good leaving groups, they're going to end up making a primary alcohol. Okay, I think I'm seeing a pattern. And then you throw this into the mixture. And you say, these don't make alcohols. What? Yeah, these make amines. How the heck do they make amines? Well, we won't actually walk through the whole mechanism. It's out there. You can find it if you're super interested. But the top reaction of an amide works similarly to the carboxylic acid. There's an acidic hydrogen here, so it deprotonates first, does some stuff kind of like that carboxylic acid. Aluminum ends up hooked up with the oxygen up here, and then that aluminum and oxygen goes away. It will go through an imine and imine, C double bond N intermediate, that gets reduced again and then stuck as an amine here. I just noticed this as I'm talking. This says acid and this gives me a neutral amine. You know better than that. If this is really acid, this should be an NH3+. Same deal down here. This mechanism, similar but different. You're going to attack the carbonyl carbon. There was air quotes. You're going to end up doing that a couple of times. What I do want you to recognize is what goes where. Let me explain what I mean. So if we highlight these H's in red, those H's are going to end up connected to this carbon through how the mechanism works. The H's from your acid workup here are going to be these H's on your nitrogen, the H's on the heteroatom. Hopefully you can picture in your mind's eye how that works similarly to the ones we have drawn. Again, these H's are going to be your heteroatom H's. Remember, these should be NH3 pluses if it's really done in acid. While these H's are going to be used to add here. Yeah? So these specific mechanisms, you do not have to know because I'm not presenting them to you here. However, If you replace these hydrogens on the original amide with carbon groups, you can draw that mechanism, and you are expected to be able to draw that mechanism because it's just like an ester at that point, but it's a little less reactive than an ester. These acidic hydrogens here are what makes things a little bit complicated mechanistically. So if you replace those with carbons, it's a simple, easy mechanism that you are expected to be able to draw. Okay. What if we replace some of the hydrogens on the aluminum with other groups? How does that change our reactivity? How does that change the product that we get? Well, we've said before, lithium aluminum hydride has 4 hydrogens. It's capable of reducing 4 groups, 4 functional groups. Well, this guy, Liatbu, this guy has only 1 hydrogen, so it's only capable of reducing 1 time. What do I mean? If you put 1 equivalent of acid chloride in with 1 equivalent of this guy, there's 1 hydrogen available. 1. So that donates 1 hydrogen to the mixture. Fold it up, make a tetrahedral intermediate. Fold it down, kick it out. Ta-da! You make an aldehyde. Where is that yellow highlighted hydrogen? It's here. That lithium aluminum hydride, nope, that's not lithium aluminum. That aluminum hydride that has had some of the hydrogens replaced with tert butoxides only has 1 hydrogen left. It only reduces 1 time. Then you might say, why the heck do I even need this acid workup? It didn't do anything. Well, aluminum becomes a Lewis acid after you lose the hydrogen. So that Lewis acid will be stuck to your lone pair up here, and you don't want that. So that water is there to clean up the Lewis acid. You ever heard me say that before? The water is simply there to clean up the Lewis acid and make sure it's not stuck to your product. Here's another example where we've only got 1 hydrogen on our group instead of multiple. These guys are very, very, very common. Instead of being written like this, it's often written as the acronym DIBOL. DIBOL, that's diisobutyl aluminum hydride, DIBOL. That little H on the end is there to kind of highlight, even in the acronym, it's highlighting there is 1 H available. So that H attacks the carbonyl carbon, makes a negative tetrahedral intermediate. Fold down, kick out, because you've got a leaving group. So it makes an aldehyde. That dibol H is over here on your aldehyde. As it turns out, you add dibol to a nitrile, you get the same dang thing. This dibol H is over here. Turns out that goes through an imine that then hydrolyzes to that aldehyde. But we'll show you that whole mechanism later of the hydrolysis. That's enough for now. Peace out, yo.